Hello everyone. So let's solve a Leetcode problem today. Today we're going to solve Leetcode problem number 200, number of islands. This is a medium problem and this is one of the problems in the blind 75 list. So the problem statement says you are given a 2D binary grid of size m into n, that means m rows and n columns, which represents a map of ones, that is land, and zeros, that is water. We have to return the number of island. So an island, this is the definition of an island. So that means we have these grids. There are like some landmarks, and then that is denoted by 1, and then water denoted by 0. So we have to find the islands. The definition of the island is an island is surrounded by water, is formed by connecting the lands horizontally or vertically. That means the lands can be connected only uh, this way and this way. Okay. So basically, you cannot connect two pieces of land, say like diagonally. This is not allowed. Okay. So you may assume all 4 edges of the grid are all surrounded by water. Okay. So basically that means this is water, this is water, this is water, this is water. So on the 4 sides, you can assume there are water. Okay. And so let's try to make this thing a little bit more visual. So let's say for the second example, you see this is a 5 into 4 grid. So m is equals to 5, n is equals to 4. Okay, now we can say like there are what can I say, like there are these points, right? So 5 columns, actually 4 rows and 5 columns. So these are the points of the grid. Now the ones that are water, I'm just making them dark. So this is water, this is water, this is water. I'm making all the waters dark. Okay. And as we know, like outside the grid, everything is water, as we said, like this is also water outside the grid. Okay. Okay. We have to find the number of islands. Now, you see, these are the landmarks, right? So there is land here. And obviously, each of these lands actually contribute to some island, right? Now, let's think from it. And as we said, these landmarks can be connected just vertically and horizontally. So let's think in this way. If we think each of these points or landmarks are nodes, right? And they have edges like vertically and horizontally. So you see there are 2 landmarks. So these 2 nodes are actually 2 landmarks. I can connect them because they're horizontally, we can connect them. And then we can also horizontally connect this, right? And also we can horizontally connect these 2 landmarks, right? Okay. So now vertically they can also connect, like 2 landmarks adjacent landmarks can be connected vertically. So you see we have a vertically here, and then, okay, that's the only place. Now clearly you see that we have like and this is like diagonally I cannot connect, right? That's clear. The landmarks can be connected just vertically and horizontally. So obviously this one is a graph problem, right? Because the only nodes that are actually land nodes, they make some difference here, or they should be considered, because only those can create islands. The other nodes actually, we just can ignore them because they cannot contribute to any island. Okay, so here we see we have nodes and edges. So how to get the number of islands? Now let's try to build some intuition. Obviously, we have to traverse through this graph, right? So traversing through this graph, and as you can see, we know different kind of graph traversal algorithms, right? And so obviously, one way can be like, we can start graph traversal, say from DFS from each of the nodes, right? If the node is a land node, and then try to go to the neighbor. So if we run DFS, it will go all the way. And as long as we can just keep on going, that means those nodes are actually part of the same island, right? That's one thing, right? And then we can actually keep on trying on each node. And one thing that we have to make sure is, like, once we're actually running, say, traversing DFS or something, right? So first, we suppose we start DFS here, right? And then we'll go here, and then here, then here, then here. And then we cannot actually move to any other neighbor. So this is island one. But what we have to make sure that next time when I will try to do DFS here again, right? I need to make sure that already this is a part of an island, so I cannot misidentify this as a new island. So what I have to do is, after I do DFS, I have to mark them as visited, right? So marking them as visited means we can just say, as a technique, we can just mark them as water, right? After we visit every land island. So these are marked as water. So next time we are not we won't try to start any DFS from there. So we'll keep on going, and then we'll try to start a DFS from here, because this is a land node, right? But this one doesn't have any edge, because it doesn't have any neighboring land, right? So this would be island number 2. And next, probably we'll start DFS in any of the nodes here. And we can move and run a DFS, and this one will become island number 3. Okay, so after identify island number 2, we'll mark it as water, so that later on it doesn't becomes identified as a new island, right? So this would be the island number 3. Okay, so the basic idea is, this problem is actually a graph problem. Each of the points is actually a node, and the nodes that are land nodes actually they make some difference, and they're significant. And the edges between the nodes, the constraint is each land node can be a neighbor to its vertically or horizontally neighbor to its adjacent land node. That's one constraint. The other constraint is around the grid, everything is considered as water. So basically, yeah. So and after we've done with the DFS, we will mark every node as visited, so that we don't visit them again. And this way, every time I can start a new DFS, that means that node has not been visited in the past. That means that node still is not a part of an island. So we have found a new island. Okay, so that's the first thing. And the second thing is, we can actually solve this problem, obviously, with BFS, because BFS also does the tree traversal, right? And as long as we have a connected component the BFS can go through, and then connected component probably should ring another bell in you, and that is we know about union find algorithm, right? So union find algorithm, one of the specialized uses of union find is of finding all the connected components. So obviously union find is also a very good algorithm to solve this, but this problem we are going to solve with DFS. We will solve other problems with union find. Another problem with union find, but obviously this problem also can be solved with union find, because the ultimate goal is finding the total number of connected components, right? So in this example, there are like 3 connected components. One is here, one is here, and the other one is here. Okay, and in the first one, you see we have just one connected component. Okay. Okay, so let's try to code this. Okay, so first of all, we have to check if we have to ask the interviewer if the grid can be null or empty. So if the grid is null, or the grid length, that means number of rows is 0. In that case, there are no in that case, what's going to happen is there would be no island, so we just return 0. Okay, otherwise we will do a for loop of I less than the number of rows, right? And inside that for loop, we will have another for loop that will cover the column numbers, right? So the column is denoted by J, and column number would be grid 0. So this row's length, right, will determine the column number of columns. Okay, so basically what is going to happen is every time we will every time we find a 1, right? So grid ij, if this is equals to 1, then we will say we'll have a variable island, the number of islands. So this one will denote the number of island. So every time we find a 1, that means a new island has started, and then we'll try to expand the island, right? So that means this is a node with a land in it. So new island has started, and then we have to run these DFS algorithm starting from this node, right? So I will just send my row number and column number, and then I have to send say the grid, right? And okay, so for the okay, so let's try to define the DFS function. Okay, so for the DFS, the input is going to be the row number, column number. So this will identify the position in the grid, right? And then the 2D grid. So when you are doing DFS, the initial thing that we have to do is you have to check if this grid point is beyond the limits. That means if this grid point is less than 0, that means we are actually going to the left. So this is out of bound, right? So if I is 0, or if I is greater than equals to, say, grid dot length, right? Or if j is less than 0, or if j is greater than equals to, not greater than equals to, actually equals to, because that's j can expand up to grid 0 dot length, and if it at some point becomes grid 0 dot length, in that case we have reached this array is out of bound, or this grid is matrix. We are actually getting beyond of the boundary of the matrix, so we cannot go less than 0, and we cannot go equal to grid length, right? Or it would be more easier to say if we write something like this, right? Because the maximum index is going to be grid dot length minus 1. Okay. Yes. So let's do this, or let's keep it like this. If any of these cases are, and then there is another case, if we have reached a point which is water, right? We stop there because there is no chance we can expand from there. We stop there. What we do is we just return. We don't do anything. Otherwise, what we do is else we call DFS on 4 directions. Okay, so we call DFS in 4 directions. Okay, and the directions are going to be, and obviously I have to send the grid. Oh, okay, so before we do that, what we have to do is we have to mark this. If this is not true, right? That means we reach this line. That means this grid point is a land grid point. But we have to first make it visited so that we don't return back here. What we have to do is we have to change this to water. Okay, we change this to water, and then we traverse to the left, to the right, to the top, and to the bottom, right? These are the 4 edges we can have from this grid point. So it would be I minus 0, sorry, I minus 1, j grid, and then I plus 1, j grid, and then the row is going to be the same, and column I am going to the right, and the last one, the row is going to be the same, but for the column I'm going up. So basically I am traversing in 4 directions, 4 possible directions, right? Not necessarily I will get to a valid point, but that checking will be done here, right? Okay. So okay, so what's going to happen is, suppose if I start DFS here, right? I will actually reach all these 4 points, right? And all these are going to be, okay, as soon as I get one a valid point, I will increase the number of island, and then I will move across and go and traverse like all the accessible land from that and change them to water. And then next time I will just move on. We'll try to run DFS from here, right? From everywhere. I will fail, and then next time I will be successful to run DFS is here. As soon as I will be successful, I'll again increase the number of the island number, right? So, okay, and oh, okay. So one thing I made mistake is this is character array. Okay. So after I like go through all the nodes and run DFS, trying to run DFS in each of them, finally I will get the total number of connected components or islands, which is the terminology for islands is being used in this problem. So return island. Okay, so let's try to run this. So what's the issue here? Okay, so my issue was, okay, so the issue here was like I had put an I here. So I fixed it, and let's try to run it. So as you can see, it was pretty fast. And so let's try to find out what's the time and space complexity for this algorithm. Now the time complexity is going to be, see how many times like we can run DFS. So basically we are visiting every node, say once, right? So if there are like m rows and n columns, right? So the now total number of nodes are going to be mn. So the time complexity is going to be order of mn. Now the space complexity, we are doing recursive DFS. So the space complexity depends on the call stack size. So say in a case where say all the nodes are 1, right? So that means there are mn number of ones. So all the nodes are going to be part of the same island. So one DFS call from here will actually cover all the, like, will reach all the nodes. So in our call stack, the maximum number of DFS calls can be order of mn, right? And that is the case where all the nodes or all the grid points are actually 1, right? So the first DFS will traverse through all the nodes, and the call stack size might get to 1. Mn. Okay, so that's the time and space complexity, and I hope this one give you a good example of a thinking of a problem which doesn't look like a graph, but you can define it with a graph and then use graph traversal algorithm to get the solution. Thanks for watching. We'll come back with another problem, and in the next problem, we'll try to solve a similar kind of thing using union.